I said, I'm a software architect at a company called Zebra Technologies. We actually manufacture, if I can get focus on the right screen, we manufacture ruggedized Android devices. So I've sort of shown a few of them on the screen here, primarily with barcode scanning capabilities. So if you need a rugged Android device, then most customers will typically come to us. Things like logistics, like postal delivery, self-scanning for your shopping, indoor retail environments, warehouse environments. If you see people with these ruggedized devices, then they're sort of invariably one of our pieces of equipment. But I mean, we've been doing barcode scanning for about 60 years now, I think it is. Or at least barcode printing. And honestly, things get a bit boring if you do the same thing every time. So we try and stay averse of like the new features that come into Android. And one thing that we were looking at relatively recently was indoor locationing with the new 802.11mc Wi-Fi RTT technologies. So we spun up a team and we learned quite a lot doing that to try and help our customers in their environments to do indoor locationing better than they had done previously. And so hopefully I can have this presentation and sort of share some of our findings with you. So I'll go over what Wi-Fi RTT is, as well as some of the like the theory behind it, and then the practical experience, which I think is sort of lacking in a lot of what I read online. So hopefully the practical experience will be the most useful. So I'll just start this off where, like, imagine the scenario if I, and I won't say those magic words, if I actually say to my, what's it called, the Nest in my bedroom, if I say, okay, turn the light on, it has the knowledge to know, hey, I'm in the bedroom and therefore I need to turn the light on. So it just turns the bedroom light on. And I was putting these slides together for this presentation, and I didn't actually know what happened if I said that same thing to my phone here. But when I tried it, it had the foresight to turn every single light on in the house, even though I just told it to turn the light on. So obviously my phone didn't have the wherewithal to know that I was in the study, and it would turn the light on up here. So a substandard experience as it stands on Android at the moment, I would describe it on my phone here. Indoor technology for locationing has existed, though, well, not quite since the dawn of man, but for a very long time. The go-to technology is this kind of Bluetooth. I think I know there was a talk yesterday on Bluetooth and Bluetooth Low Energy, where you have Bluetooth beacons advertising their packets, and the phone or the device can know, hey, I'm close to this beacon, therefore like I must be in this room, or I'm close to these couple of beacons. And the difficulty there is, you're close to a beacon, and it's kind of a GUI, globally unique identification, isn't it? But what does that actually mean in the grand scale of things? Like, okay, I'm near this particular ID, but where is that ID? Where is, am I left, right, up, down of that ID? What floor am I on? Those kind of questions are not answerable just through standard the standard interface of BLE. But it's not just Bluetooth. There are a plethora of location systems. In fact, we've got a whole division. I'm not part of that division, but we have a whole division dedicated to locating devices as well as people in both indoors and outdoors in our company. And we use like ultra wideband radio frequency. There's RFID based solutions, and you'll find this on particularly like high value airplane parts and stuff like that. They'll sort of tag everything with an RFID tag, so you know where this stuff is. There's new companies coming in, and you're sort of seeing a melding of Bluetooth and Wi-Fi and virtual beacons. I know that Mist has that technology, and Wi-Fi locationing. There's network systems like AP manufacturers like Cisco have their own locationing systems based on the signal strength of the router, and you can sort of triangulate the location of the user based on the signal strength. How reliable that is depends on whether you trust the marketing or whatever. And obviously there's the whole COVID track and trace. Am I close to someone else who's had COVID? And that is a BLE, and I've seen various reports on the accuracy of that is. We have our own locationing solution called MotionWorks Proximity, which can use a similar technology to determine if you've been near someone. But all of that is immaterial to what I really want to talk about today. I just want to emphasize that an indoor location solution overall doesn't exist on its own. I said like the BLE beacons need to have a well, it gets the ID, but what does the ID mean? So you invariably have some kind of back-end component. There's a map. You have to provision this beacon to say, hey, this beacon is in the study, and then the phone or whatever it is needs to download those maps to present the maps to the users. The phone can't do everything itself, and that still remains true. And I want you to sort of remember this principle as we go on and talk about what Wi-Fi RTT and 802.11mc is. So in a nutshell, and this slide has been around for a couple of years now, so the technology itself isn't new, but adoption has been quite slow, and I'll go into why that has been in the future slides. But it's called various names. I'm going to use these interchangeably. FTM or Wi-Fi RTT was sort of used in the Google Docs. Supported in Android from Pi Plus, which is where it really came to the fore in most of the developer mindsets probably on this call. It works by essentially timing the time that it takes for a signal to propagate from an access point to the mobile device and then back again. You get that round trip time, hence the RTT in Wi-Fi RTT. You can subtract the two. You know how long it's been in between sending and receiving that message, and therefore you can work out how long it took that signal to get to the Wi-Fi access point. And based on the resolution of these calculations, it's very accurate. It's more accurate than we've seen, in theory, in some of the like competing standards out there that also use the signal propagation time from an access point to your device. So the resolution is about 1 nanosecond, and when you work it out, it comes to about 30 centimeters is the theoretical resolution of your location indoors, which is amazing. That's like, I can probably get it on camera here, like 0.3 meters, a foot. Choose your measurement systems. Wouldn't that be amazing if you can work out your position to that level of accuracy? So it is really exciting for a lot of people, and there's a lot of interest in the industry. And I've seen that kind of die down recently, but I don't think it should do. And the reason is, when this was first introduced, there is a lot of things that you need to have in your stack in order to use the 802.11mc. So it needs to be supported by the access point. And when I first put this slide together a couple of years ago, there were only 2 access points that really officially claimed support. I mean, maybe they're famous in the industry. I'm not a networking engineer, but I'd never heard of them. So these 2 up there, probably embarrassed myself. They're probably very famous. You did have some kind of rudimentary support with the mesh routers, the Google mesh routers as they were at the time. You needed to have support in your operating system, so it's supported from Pi, and also your network stack on your phone needed to support it. So as an example, it did work on my, well, this is my Pixel 4, but my Pixel 2 at the time did work, whereas some of the other like devices we had for work didn't support it in the network stack at the time. So that was where things were a couple of years ago. What has happened recently, though, is I talked about only having support in those 2 access points. What actually happened is support was added into both Broadcom and Qualcomm at the time, back in 2018, and most access point manufacturers use these system-on-a-chip providers to, for the innards of their access points. But the feature, although it was present in the chipset, was not turned on. The reason for doing that was like competitive, proprietary reasons. If an AP manufacturer has got their own location technology, they don't want to enable the support of a competitor. It's just common sense. It's how the world works. And yeah, we saw these things turned off for quite a while. But what has happened more recently, we've seen like industry, and when I say industry here, I mean like really big customers, big retail environments, big retail customers who are refreshing their hardware. Like they get new functionality comes along, things like Wi-Fi 6, and they're buying a whole load of new kit, and they've got a lot of pressure that they can put on these hardware manufacturers, and they're saying, hey, we would like you to enable 802.11mc, and then we will buy your kit. And they've got the kind of buying power that enables them to get that work done. And we recently announced that Aruba is adding 802.11mc support to their routers, and we envision seeing this rolled out to other access points as well further on down the line. And yeah, so it's good news as far as access point support is concerned. So that this is a screenshot from the Google documentation. Top of the very bottom, I've put the link there, the supported devices for Wi-Fi RTT. The access points list, that hasn't changed. That's kind of, where's my hand there? So it's kind of still those 4, but envision that get a lot bigger. What we are seeing recently, though, is that original list of Android phones that supported 802.11c has gone from 10, 20. It's now at over 340. That was the number from Google. I didn't sit there and count all these individually. I don't know how, but I seem to have reverse alphabetically ordered this list. So we've got all the Xiaomi models there. This is not a specific Xiaomi feature. This is just part of the Android operating system, as long as the phone's network stack supports the feature. So obviously this list goes a lot further down than what's showing here. So we've got the phone support, we've got the access point support invariably, and I know at this point in the presentation it's probably getting a little bit dull of me just talking about this feature, so it'd be nice to actually show something. And I thought the first thing which would be interesting to show is, like I said, we had a team that was looking into this. Most of these teams are in the US. We're a US-based company. I'm just in the UK because I'm the outlier. And so we wanted to sort of demo this product to some of our retail customers. Is this something you'd be interested in? You know, we're not selling access points, but we want to provide value on top of our devices. So we set up a sort of simulated area. We had a lot of shelving and items, and I'll show you the video momentarily. I'm just trying to set the scene, bear with me. And the operator that you'll see in the video has a Google, I think it's a Pixel 2 device, and we have 6 Google Wi-Fi APs set up like a 6 on a die, you know, 222, I believe it was, and they made some assumptions with respect to height off the ground on the device, and I'll get into sort of the calculations in a subsequent slide, but there is some proprietary algorithms and of calculating the user's position based on the distance that's being returned from each of those access points. So if I just play this, hopefully the video is coming through on the casting, but if it's not, then I'm going to be describing this as it is. So you'll see the operator is walking at a fairly constant speed, and on the left there you'll see the little zebra head logo. That's their calculated position on the map. Now that was quite smooth going down the aisle, but notice when they get near the wall, near the shelving, it gets a little bit jittery. You get like things called signal attenuation, and the signal's bouncing, and so it gets more difficult to locate the user in that environment. But now they're walking back up the aisle, they're more in the middle, and they're being tracked quite well at this point, only to get to the end of the aisle, and then, you know, things get a little bit bouncy, as it were, with regard to the measuring the distance to the nearby access points. These access points are off the ground. Notice how every now and then there'll be a jump, like maybe the calculations are wrong somehow, or things have changed. And now the operator is stationary, and we're seeing some jitteriness around the little zebra head where it's being calculated. So quite a lot to take in there. By and large, though, that was a reasonably open plan environment, and the results were good-ish. Obviously, you know, we tried to make this realistic for our customers. The takeaways were, when someone was standing still, you still had that jitteriness of the algorithm. Maybe that could be filtered out. I know they were using a Kalman filter for that. And also, when they got next to the metal shelving, you sort of had some it jumped about a little bit. So let's move on. I just want to talk about what that sample app that you just saw was doing. So this application was running, I want to say it was running on Android 10, but it was built to API level 28. So there have been 2 major, well, there's been the introduction of the feature in Android Pie, and then there's been an additional set of APIs added to Wi-Fi RTT that came in Android 10. So in Android Pie, you had like 3 classes, or there's a couple more, there's like 5 classes there, isn't there? Essentially, you get the ability to detect from your Android application the distance that you are from any particular access point. And I'll show this in a couple of slides. So you have like the Wi-Fi RTT manager where you can create and initialize these objects. You can create a ranging request against a specific AP. Obviously, you've had to scan the nearby access points and you've been given the location runtime permission to do that and all the great new things that have been added to Android privacy that we've heard about earlier on in the day, and then you get a result back, and the result, excuse me, will tell you the distance that you are from that particular access point, as well as the standard deviation of that distance. So the standard deviation is essentially a measure of error. I did do statistics oh my gosh, so many years ago now, but I remember a few of them. So that was pi. You had the ability to detect the distance to APs. In Android 10, you are given the additional ability to pre-provision those access points. And again, I'll get into this a little bit subsequently, but it's all very well and good knowing that I'm X meters away from a particular AP, but where is that AP? Where is that access point? So the addition in Android 10 is essentially being able to program the access point and tell it, hey, you are here. I'll go into that in subsequent slides. I did think it was worth just dwelling a little bit on the sample app that's available from Google. So they've moved it about a couple of times. Obviously, that link's a little bit old. It's no longer on the master branch. It will be on the main branch now. But the key that I want to say here is what's in GitHub will give you the ability to scan for nearby APs. It will tell you how many of those support Wi-Fi RTT. So I actually got 4 of these mesh, like the Google Nest APs. So it returned 4. My router, I'm currently using like Sky Broadband. It's actually downstairs. That was not supporting. So it wasn't shown. I didn't have the option to range off of it, which is fair enough. You know, the router doesn't support it. Many don't. And then what you see back is in the middle screen there, it gives you a range in meters as well as the standard deviation of that range. And then it's doing some calculations. This is the first thing that I really want to stress. If you look at, that's like a representative result that you're seeing there on the third line down. Well, you can't see where I'm pointing on my screen, can you? The third line down, 1.33 meters standard deviation. Now, remember, the theoretical was that 1 foot, and now we're well off of the webcam. We're like, what is that, 1.3? It's a lot bigger than what it's supposed to be theoretically. So, and what you'll find is that will change from reading to reading, and that jitteriness that I was showing in the previous video, hoping it came through, was a result of these readings changing, even though the user doesn't always change. And okay, well, yeah, we'll get into some of the reasons why that might be in a subsequent. But yeah, this is what you can do with the Google sample app on GitHub. It works, you know. It shows you it working as long as you've got all the hardware. If you download the thing from the Play Store, this is true as of like a week ago. I tested this because I was surprised they didn't update their GitHub repository, but it seems that the application on the Play Store is more functional than the application in GitHub, and it has all of the Android 10 edition, so the ability to provision an access point to be at a particular latitude and longitude. You see sort of in green highlight at on the second screenshot there, and these screenshots have just been taken from the Google Git the Play Store page, I should say, from this. So all copyrights to Google or whatever here, but yeah, you've also got some logging you could turn on. But just to make you aware, if you are thinking of trying this yourself, there's 2 apps that you can download from Google to try this with. So I said it's easy to do if you've got the right hardware. So I did put together a very brief video to sort of show this working with the sample app. I do have my own sample app in subsequent slides, but let me just show what this does. This is with a single Google Wi-Fi access point and a stationary Pixel 2 device running Android 10. So it's stationary, that's key here. So this demo is sort of fine for showing available values and getting a rough distance. It's not designed for really more than that, to be honest, just understanding the technology. First thing I do is to enumerate nearby access points. I must have been watching Lord of the Rings when I named these things. But now it's returning the values every second. That's nowhere near frequently enough. You want to return them as frequent as possible. and then like scan, and you'll get results back reasonably quickly. Where you can see them coming through on the UI here. Notice how even though I'm stationary, it's going between 3.6 and 3.5, maybe 3.4. The standard deviation is quite low. Bear in mind, though, that if your user is moving, then obviously the number of readings that you want to take, you want to average them. So I'm taking loads and loads of readings there. They're jumping around. I want to average them. If they're moving, then I don't want to make that average of too many readings, because then, this is old data over here because they've moved. Whereas like the more readings I can take in that average, the better, because it makes things a little bit more reliable. I'll talk about averages as well. So I touched on this question earlier on. It's all very well and good knowing, like in that example there, that I was 3.4 meters away from the access point, but where's the access point? Where does that mean? Like, what good is that of knowing that piece of information to me? And you get into the same kind of issues you had with the old BLE beacons. That ID is in the near Primark. Well, in a retail environment, I don't know. So where am I? So first thing, it's worth mentioning, the sample app will use the arithmetic mean to calculate, so of the last 5, it's configurable, but of the last 5 readings, give me the mean of those. That's the standard mean that everyone learns in school. It is better to take the weighted mean. So a weighted mean will give you the ability to incorporate the standard deviation into your mean calculation. And I've said a couple of times now, what you get back from the API is a distance as well as a standard deviation, a measure of error. So we have the information, so why not use it to give ourselves a more accurate version of the mean? So yeah, use the weighted mean. I got that from Wikipedia, honestly. I'm no statistician. I did do my final year university project in statistics, but not as complicated as some of these libraries we'll get into previously. So shortly, we're talking about multilateration now. So this is like with the one access point example, and I knew that I was 3.5 meters away. So I know I'm somewhere within that circle around the access point. I could be anywhere though. Who knows? My device doesn't know. It just knows a single distance with a reading of error. It could be anywhere. So now I need to introduce a second access point. So I only showed one in the demo previously, whereas you can actually range against multiple access points at the same time. And in this scenario, I am about the same distance away from the red access point, and so I know that I must be in one of these 2 positions because I've taken away all of those degrees of freedom. And the third thing, obviously, I need to do is then range against a third access point, and now I know that I am definitely in this position here. So in a 2-dimensional plane, I need at least 3 access points to range off of. But in 3 dimensions, things get a little bit more complicated. These are supposed to be spheres. I'm not an artist, but this was me trying to say that in 3 dimensions, you could, in theory, have 3 access points and have 4 access points and take 4 readings, and obviously the number of access points goes up. It's 1 more than the number of dimensions, but we all live in the same universe of 3 dimensions, so we're not going to get more than 4. What I did see in my tests, and my colleagues saw in similar tests, we were using the Google Wi-Fi access point, and it was unreliable in 3 dimensions. Like, it was fine. Let me just try and get this on camera. If you were measuring like in a 2-dimensional plane, that was fine. If this is the access point, this is my device. As soon as I moved above the access point, things got very unreliable. You imagine the distance should get more, Pythagoras theorem, right? The distance actually got less, and that gave me less assurance on the reliability of some of these things. If you have anything in the way, obviously signals can bounce around. They can bounce off the ceilings, they can bounce off the walls and the floors. So what it's measuring is the time it takes. It's not always going to be that direct time. It might be the bouncing off and coming back, and that can get unreliable, particularly where there's a lot of stuff in the way, like that warehouse environment where they were near the walls I was showing previously. But back to multilateration, I I took advantage of, and indeed my colleagues found this independently, I don't know if this is a man or a woman, but the Lemming Apex library for trilateration here. I've taken this image from their library. It was released under, I can't remember if it is MIT or Apache, but it was a fairly permissive license. It was certainly, certainly good enough to allow me to incorporate this into my sample application and to make use of it. And what this library gives you is you can pass it in a number of locations of access points, and you can tell it the number of distances to those access points, and it works in any dimension, and it doesn't have to be access points, obviously, but it will calculate the most likely location of you. And just to go back, this slide was showing like a perfect example. Real life is never that perfect, and like even previously, like it was ranging between 3.3 and 3.6 or something, wasn't it? So these are going to be moving circles around here, and this library did its absolute best to sort of give you a best guess of position. I mean, what it's trying to show here is a red dot in the in a fairly realistic scenario there, where not everything overlaps identically. So imagine when I was first asked to give this presentation at a Droidcon, I was very happy. I was going to be traveling to Turin in the good old days, and meeting all you great people. And I was going to be up on stage, and I was going to do a live demo. And it's still worth keeping this slide in though, because it shows a number of the issues that I was going to have with this demo, as well as like the type of issues that you would see in real life as well when you try and do a rollout of Wi-Fi RTT. So I guess I could have, the first thing I was saying is I'm using a 4.5 meter USB cable from Amazon. I didn't have to. I could have used like Wi-Fi screen share, but I didn't want to use Wi-Fi over the conference Wi-Fi. But I just wanted to say, if you do your own tests, most people, if you do it now, are going to go for the Wi-Fi access points from Google. They're like $100 or pounds each, so fairly pricey, but not overly pricey to sort of play around and have a go with this technology. But they are designed for consumer use, so they're not designed for kind of enterprisey use cases. They are being powered over USB, so just bear in mind they're designed to have a proper power supply given to them, and they're very close together. And this is a key point. In my demo, they were going to be very close together, but you get a more accurate reading of where you are the more distances you can incorporate into your calculation. So if I have a mesh of 10 access points, then I get 10 distances and I get a reasonably reliable location of where I am. But of course, if I have 10 access points all that close together, they're going to interfere with each other. There's going to be lots of signal bouncing and propagation, and I forget the other word for it, but that's going to introduce error rather than introduce accuracy. So those are way too close together. Signal attenuation, like I said. The other thing is there is a minimum distance required to actually range off these things. So if you're anything like me, the first thing you'll do when you get one of these access points and you download that Google sample is you will get your phone and you'll tap it on the access point, and it doesn't read 0 because you'd think I'm 0 meters away. That should work. No, it told me I was like minus 2 feet away or whatever, and yeah, that was a bit strange. So just make sure whatever calculation you're using, even if you're using the trilateration algorithm I discussed previously, you do also need to make sure that there's no non-zero values in there. Well, depending on your coordinate system that you choose. So, oh yeah, and everything just stopped working a month before I put this slide together. This slide's been here for a couple of months. So that's all very well and good. I had these things in a line, I think it was, and there was like one behind me as well. And this is not the best layout for it. You get you want to have a layout of your access points where the smallest variation of movement from you will lead to a difference in distances to the access points. So imagine if these things are all in a line and I'm out in the front here. If I move a little bit, my distances to these access points don't really change that much. Whereas if they're kind of in a a square and I'm in the middle of the square and I move slightly within that square, then all of these are moving in sort of in tandem with each other, and it gets a lot easier to calculate. So that's another thing to bear in mind. Make sure you're putting your access points in sensible locations. So I talked about Android. This is done with the Android Pie APIs. I didn't use any of the Android 10 LCI APIs that I'll come on to in a couple of slides. So I had to define my own coordinate system. The first thing I thought to do, naively, was, okay, I will get my access points. I'll put them around the house or on the stage or wherever I was going to be, and I will work out their lat long, and I would use the World Geodetic system, that WDS84 system, to sort of say, okay, well, there's the lat long, and I can pass all of those. I think I had to convert them to Cartesian coordinates and pass that into the trilateration library, and I'd get back my location. Job done. That's easy. It's not quite that easy though, because you need to sort of know where the access point is in a lat long, and that's not easy to do. I should have. Oh, they're in the cupboard up there. I should have got one, but like it's indoors. The best thing you can really hope to do, I think, is to look on Google Satellite View and then work it out like meticulously with a ruler or something. Make sure you turn off three-dimensional view or aerial view, because that's going to mess up all of your coordinate systems. That happened to my colleague. I wouldn't advise that. She wasted a lot of time doing that. Yeah, that was not a happy day for her. But yeah, make sure you turn that off. But anyway, so I'm rambling now. I want to get on to the demonstration. So I have an application which I put together. I am not a graphic artist by any means, and so all this is really doing is calculating my location based on these there's four access points here. There's one not shown in the image there, but was there four or three? There might be three. Anyway, let me show you what this looks like in this video demo. And this was what I'd ideally like to have done live for you. But you see, I see that same jitteriness as I was talking about previously with my colleague in the simulated warehouse environment over in the States. And it's reasonably accurate. Like it knows I'm within these bounds, but sometimes it darts away. And there's only so much that I can blame my algorithm for that. I'm sort of passing in the same readings that I'm getting back, and most of the time they're reliable, but sometimes they go off on a tangent. I'm not moving very quick. I'm mostly slowly, but I am mostly still, but I am slowly moving around these access points. I don't want to get too close, because like I said, that will give a negative result, and so I'm sort of accounting for that. But yeah, it works. Feel free to download this, have a play for yourself. If you've got a mesh network in your own home, this probably works out of the box. Obviously, you won't have the access points set up. Maybe you do. You can modify the code and define your own coordinate system or whatever. But yeah, there's enough code here to get started playing with this. So I did most of my experimenting with Android Pie, and then in Android 10 they introduced these responder location objects, and I sort of touched on these earlier on in this presentation. So the ability to tell the access point which latitude and longitude it is, and at that point, how do you know that sort of stuff? It gets difficult, particularly with altitude. Like, you can get altimeters, but they rely on barometric pressure, don't they? Once you get into this kind of field, you realize there's a lot that you don't know from my experience. You guys are probably cleverer than me. So what is most useful though about the Android 10 feature here is that use case that I touched on right at the beginning of this presentation, which is like the BLE environment, and I have my device and it knows that it's next to BLE ID, whatever on earth that means. Now, because you can provision your access points with useful information that your device understands, well, if I can somehow work out that the access point is in this lat long position, then I can tell it that, and then the device will know, well, it has context of that. Maybe it can use the geolocate or Google Maps API or Huawei Maps that we were talking about earlier on in the presentation in the day to determine like where the device is. It doesn't need to use that back end mapping, custom, expensive thing to develop. It's all on device. It's very quick, and you don't have to have that pre-provisioning step. You do still need to trilaterate your own position though. Like if I know I'm 5 meters away from that AP, which is at that long, and I'm 10 meters away from that AP at that long, then where am I? It's the same question, but the same libraries exist. It's not just that long. You can also provision an access point with a city, country, building, desk, postcode, which becomes very useful in indoor environments, particularly with height. As Marco mentioned earlier on in the call, how do you know what floor you're on? That's an ever-present problem with indoor locationing. And now I can know the floor information just by asking the access point. The sort of averse, the other side of that, though, is the device or the API will blindly trust whatever data is in that access point. And coming from an enterprise environment, that made me a little bit wary because there's a lot of potential for mischief or harm. I don't know how much harm you could really cause by telling a phone that it's at a slightly different place than it actually is. But hey, we've seen rockets break apart with similar information. And actually, I think they did remove the ability to have a custom location provider in Android, or you need to have special permission to write one now, whereas that was something that we previously able to do. Anyway, again, I'm rambling and I apologize. I want to get to my conclusions for this presentation based on my experience, based on my colleagues' experience, is the technology is interesting, but it provides nowhere near that maximum 30 centimeter accuracy like that. It's more like bigger. It really does depend on your circumstances, what you're near, where you are in the building. It talks about its indoor locationing, but at one point I've got the flimsiest doors in the world. I'm trying to, like, my door is over there. I closed my door. It's like 2 sheets of plywood or something, and the API didn't know where. Like, it got completely confused. Which, okay, maybe that makes sense, because how is the signal getting to my phone from the access point? Maybe it's going under the door. I don't know. But yeah, it couldn't cope with a flimsy door, so it's certainly not going to cope across multiple floors. Compare that with the ease of use of the fused location provider, for example, where you can get your position outdoors in a single call. In fact, one of the things we have worked with our customers to do is to try and address, like, okay, even if you're not using AO211MC, can you use the fused location provider indoors? And the findings that we've got is that it's probably good enough if you need to know whether you're in, like, a certain department of, you have these huge department stores. If you're in a certain department, then you can probably find that out using a fused location provider. But a lot of that will be dependent on how well Google have surveyed the area. So maybe you're in the nails section or the plumbing section or something. But anyway, I'm getting off topic. What I'm saying is, don't take my word for it that the locationing technology is good but not quite there. There's a great paper written by Mr. Horn from the MIT, Cambridge, Massachusetts, and he goes into a lot of detail on more of the technical aspects that I'm an Android developer, so I don't really understand RF signal propagation, radar frequencies, all that kind of really interesting stuff. But I did want to highlight some of the things from his extract, which says the standard deviations of 1 to 2 meters, which I sort of saw in my testing, is in favorable circumstances and limits the range of applications. You can't use this where there's like multiple buildings, or for like things like fire rescue workers. That doesn't really work for those kind of use cases, because you have signal delays, propagation delay, things I don't understand, like high relative permittivity of construction materials. So all that information available from that paper. So please do take a look. Relatively recently, I think it was this year, January this year. So with that, I have provided my slides to the organizers, so all of those links are available, and I'll go to questions now, please, if there are any.